Let's continue our chapter 7, energy, work, and power. At the beginning, today we want to talk about work in uniform circular motion. Do you remember uniform circular motion? We talked about it in the previous chapter. We said uniform circular motion, it is the motion of objects moving in a circle with constant speed and changing velocity. Constant speed, it means the magnitude of velocity is constant. It's not changing all the time here. We said the object is moving with the same speed, 2 meters per second, 2 meters per second, 2 meters per second, all the time. What is the only thing changing here is the direction. Direction is changing, and always this direction is tangent to the circle. At any point, it's tangent to the circle, okay? The second thing about uniform circular motion, that centripetal acceleration and centripetal force, they are always directed toward the center. So, tangential speed and centripetal force, they are perpendicular to each other at any point, here or here or here or here. At any point, they are perpendicular to each other. Okay? And we know that velocity depends on what? Displacement. V equals d over time. So, do you think that we have work in uniform circular motion? We don't have work. You know why? Because we said work, we have it when we have force and displacement and they are parallel to each other. If they are perpendicular to each other, work equals 0. So here is an example or a case for work equals 0. Because all the time in circular motion, the displacement and force, they are perpendicular to each other. So we don't have work. Clear? In all cases for uniform circular motion, work equals 0. To understand it more and more, let's use the work kinetic energy theorem. You remember it? Work net equals a change in kinetic energy. It equals kinetic energy final minus kinetic energy initial. Kinetic energy final half mv final square minus half mv initial square. V final is what? Let's say here it's 2 meters per second V final. V initial is what? 2 meters per second. Why? Because all the time in uniform circular motion, the object is moving with constant speed. So, half mv final square minus half mv initial square, the answer is what? 0. Is it clear? Did you believe now that work equals 0 in uniform circular motion? Good. So if you see uniform circular motion, always work 0. Why? If I ask you explain, you just say because force and displacement are perpendicular to each other and we don't have work when the force and displacement are perpendicular. Okay? Now, again, the name of our chapter, energy, work, and power. We talked about energy, we talked about work, now we want to talk about power. What's the meaning of power? Power is the amount of work done over a period of time. How much work done in a specific time. So what do you understand? Work over time. Power equals work over time. This is the formula for power. Another definition. The rate at which work is done. The rate at which work. Instead, always when you see the word rate, what comes to your mind? Time. Something related to time. So the rate at which work is done, it means work over time. Another definition. It is the rate of energy used or energy generation. It's okay because we know that work and energy, they are what? The same. So it's the rate of energy transfer or energy use. Okay? Let's look now. Here is the formula for power. Power equals work over time. The unit of work is joules. The unit of time is second. So what's the unit of power? Joules per second. Joules per second. What equals? it equals watt. We call it watt, okay? So the unit of power is watt. 1 watt equals 1 joule per second. Okay, girls, here is the main formula for power. But sometimes in questions they don't give you the work direct. What do? They give you the force and displacement, and they ask you for power, and time, and they ask you for power. So what do you do in this case? You just find work first by multiplying force times displacement, then you divide by time to find power. There is another formula for power. We can find power by multiplying force times speed. Look here up. Force times distance over time. And we know that distance over time equals what? Speed. That's it. So it's not a new formula, girls. It is not a new formula. Force times distance over time. You have to memorize this main formula for power and this formula for power. Okay? This one, you can know it by yourself. You know that work equals force times distance, so you can use it when you need it in any question. Okay? When you look at the top of a light bulb, it is labeled in watts. Look here, when you go and buy a light bulb, you see that here there is a number written with W, 40 watt. A watt is the rate at which the light bulb uses energy. What does it mean here, 40 watt? It means that this light bulb uses 40 joules of energy every second. Okay, this is the meaning of 40 watt light bulb. If you have a 100 watt light bulb, it uses 100 joules of energy every second. Okay? The last thing I want you to know about power, that power is a scalar quantity. It has no direction, just a magnitude. We don't say 40 watt to the right or to the left or whatever. No, it's a scalar quantity. Okay? The same as work. Work is a scalar quantity also. The difference between work and power. Now, work represents the amount of energy transferred when doing something and when you are moving an object from here to here. What is work here? I want to see how much energy has transferred from kinetic, for example, to potential, or from potential to kinetic. That's it. The amount of energy transferred. Power is what? Represents how fast energy was transferred, how much time takes until energy transfer, okay, from one form to another. This is the difference between work and power. Let's together solve an example about power to see how do we use the formulas in solving problems related to power. Determine the power required to lift a 10 Newton crate up to a 400 centimeter high shelf in 2 seconds. So here's the question. They want you to find power. What I have? 10 Newton. This is force. So I have F, force. 400 centimeter high. I have distance. But the distance it's given in centimeter. We can't use it in the formula. We always use meter. Okay. In 2 seconds, I have time. So it's easy. What I'm going to do? Power equals work over time. But the first step, we have to convert centimeter to meter. How? By dividing by 100. So the answer is 4 meter. From centimeter to meter, the answer is 4 meter. This is the first step. The second step, write the formula. Power equals work over time. We don't have work, so we need to find work first, then we find power. How? By using force times distance. I substitute now 10 times distance 4, remember to use the converted distance, over 2, and the answer is 20 watt. 20 watt or 20 joules per second. Okay? You have here 2 examples, solve them by yourself, and tomorrow I will send you the answers. Now we want to talk about conservation of energy. For sure, you all know this law. We took it before. Energy cannot be created or destroyed, but it can change from one form to another. Energy is always conserved in an isolated system. What does it mean, isolated system? When we say isolated system, it is an ideal system. We don't have it in real life, but it means that we don't have friction, no air resistance, and these forces. So, when we have an isolated system, energy is conserved always. It means that the amount of energy present at the beginning of the problem must remain constant throughout the entire problem. This is the meaning of energy is conserved. The same amount of total energy stays all the time the same. Let's talk about some properties of energy. The first one, that energy can transform from one type to another. It means that energy can change from kinetic to potential energy, from elastic potential energy to kinetic energy, from chemical energy to kinetic energy. Number two, energy can transfer from one object to another. When I push an object, the energy is transferred from my hand, from my body, to this object. So energy, it can transfer between objects. Energy can leave and enter a closed system as work. This is the third property of energy.